All right, here we go. Yeah. Not today, because I have some people that have been absent, like Alicia, that still needs to make it up. So once I have the makeups done, I should be able to pass those back. Conceivably, that would be Friday if this class meets on Friday. Does this class meet on Friday? Okay. Friday, potentially, then. All right. Stop talking. Those of you that remember anything about trigonometry from geometry, remember that SOHCAHTOA. And SOHCAHTOA operates on an angle measure. So we need to talk about some angle stuff here to start with. In geometry, when you measured an angle, what did you measure it in? Degrees. So our first order of business here today is going to be creating an alternative measurement to degrees. Angles in trigonometry. So let's say we have a central angle here. So when we talk about a central angle, what we mean is the angle whose vertex is at the center of a circle. Everybody remember that from terminology from geometry, at least after a little bit of a reminding? Okay? So we're going to create a new measurement for angles. So if we have a central angle, we're going to say that has a measure of 1 radian. That's going to be our new measurement, our radians. If it intercepts an arc with the same length as the radius. So in our picture here, we would say that if the segment AB is congruent to the arc CB, and remember, for arcs, we give them a hat that's like arced, then the measure of the angle CAB is 1 radian. So we have this new measurement called a radian, and this measurement of a radian is basically relating angle measure to the length of this arc intercepted when we embed our desired angle inside of a circle like this. We have another measurement of an angle that we had from geometry class, which was using degrees. What we'd like to have now is a way to convert from one to the other. So what we're looking for is a way to convert angle measures to degrees. Everybody okay with that plan? Okay. So let's imagine the following situation. So let's say we have some circle. And let's say that this is our central angle here. And let's even be a little bit more specific and say that this is a unit circle. That is, that the radius of this circle is 1. Everybody okay so far? In degrees, what does this angle CAB measure? 180 degrees. What is the arc length from C to B? Pi. Remember, the circumference of a circle is 2 pi r. So the whole circumference is 2 pi r, where r is 1. So the whole circle is 2 pi. We're only talking about from C to B, so we're only talking about pi. Okay with that? So what I can say then is that 180 degrees is equal to pi radians. That's my conversion factor that I'm going to be using. So notice when I write pi radians, there's no degree symbol for radians. The unit that we write there is just radians, or oftentimes when it's clear from context that we're talking about radians, we don't even write radians. So we might just write, angle, the measure of angle C is, like 3 over 2 pi. And it'll be understood that we're talking about radians there. Is everybody okay with that from a notation standpoint? Okay. So let's do some examples where we convert from radians to degrees and vice versa. So let's say I want to convert 90 degrees to radians. So I'm going to start with what I know, and I'll multiply this by a conversion factor. The conversion factor that we have for radians and degrees is that 180 degrees equals pi radians. So how would I write my conversion factor here? What part is going to go in the denominator? 180 degrees. And what part is going to go in the numerator? Pi radians. So just like the unit conversions that you've done in your chemistry class or other science class, you remember that things with the same unit line up diagonal from each other. So the degrees part can cancel out. And when I multiply across, I'm left with 90 pi over 180, which reduces down to just pi over 2 radians. And if you didn't write the word radian there, that would still be okay. Everybody okay with how I've done that? So you notice here when I wrote my radians, I wrote them in terms of pi. That's usually quite desirable, but it's not necessary. So for example, maybe I want to convert 151 degrees to radians. Is there really any difference between this problem and the previous one? No. Not initially with our setup. But what do we notice about 151 pi over 180? Does that reduce? It doesn't, does it? So we might want to leave it in the exact form it's written there. Or we could type this into our calculator and provide a decimal approximation. This is also a perfectly reasonable representation for radians. Everybody okay with that idea? So you do need to be careful because sometimes we'll write radians as a decimal. So if you see 2.635, you should recognize that as an angle in radians. If it was 2.635 degrees, that's something different, right? Raul? You do not need to change the mode in your calculator to do the conversion. Yep. So that's a good question. When we start using our trig functions in the next section, we will have to be very careful about that. But for right now, we do not. Not to do conversions. So let's say we want to convert 2 pi over 5 radians to degrees. Again, I'm going to start with what I know, which is 2 pi over 5. And then I'm going to multiply it by some conversion factor. What should be the denominator of this conversion factor? Pi radians. And the numerator should be 180 degrees. So when I multiply this out, I get 360 over 5, because the pi's are going to cancel, which simplifies down to 72 degrees. Everybody feel so far so good? Do one more just to be careful about things. So let's say we have 1.6 radians, and we want to convert that to degrees. Does anything really change from my work above? Not really, right? The issue here is that there is no easy canceling that I can do. Would it be really standard to write my degrees in terms of pi's like that? No, right? I'd want to type this into my calculator and get a decimal out of this. And I guess I should probably write that as a squiggly. I rounded. So you notice that I'll try to be consistent using the squiggly equal sign when I do any rounding. And I'll use the hard equal sign when it's an exact answer, when there was no rounding that took place. Bella?
So do you want us to read out some places?
Sure, if not otherwise stated.
Okay.
So usually we'll be clear about where to do the rounding.
Okay.
Okay. Everybody okay with this idea? All right. So let's move on. So let's say if we have a central angle, and let's measure that central angle in radians. And the variable I'm going to use to describe Can I finish speaking before we jump all over this? Okay. So if we have a central angle that we're going to measure in radians, the variable I'm going to use to describe that measurement is the Greek letter theta. Oftentimes in trigonometry, we use the Greek letters to name our angles. And the most common Greek letter we use to name an angle is the Greek letter theta. It just looks like a 0 with a horizontal bar through it. Is that answering your guys' questions that you were getting all feisty about? Okay. I was getting ready to say it, and everybody just got stuck on that he didn't tell me what that symbol was that he just wrote. Okay. Continuing on. In a circle with radius r, then the length of the intercepted arc is given by S equals r theta. And maybe we should say the intercepted arc S. So what's the really important caveat about this formula? It's that this angle that we're using in our formula must be measured in radians. What would I have to do to this formula in order, or if my angle was measured in degrees? What would I have to add on, or what would I have to do to this formula? Yeah, I'd have to convert it into radians, which means I'd have to multiply by theta by pi over 180. Sam?
S is the length of the arc, right?
Correct. Yeah, I added it in there. So if my angle measure was given in degrees, I'm going to use the formula. S is equal to pi r theta over 180 degrees. So let's do some examples where we use this formula. I just simplified it, right? Suppose we want to solve for S if r is 1.4 meters and theta is 0.98 radian. Which of the two formulas for S do I want to use? The first one or the second one? The first one. Why do I want to use the first one? Because my angle measurement is in radians. So I can just plug this in and type it into my calculator. And the unit that I output here should match my unit of length on the radians. That's pretty easy, right? Suppose we were asked to solve for S if the radius is 3.8 inches and theta is 40 degrees. Which of the two formulas for S should I use here? The second one. In this case, we're going to have pi times 3.8 times 40 all over 180. And when I type this into my calculator, I get about 2.653 inches. Everyone okay so far? Hopefully this feels pretty easy, right? All we're doing is just typing stuff into a formula. Not too tricky. So we'll do another here. It says solve for r if s is 18 degrees and theta is 2.63 radian. Oh, I'm sorry, 18 centimeters. Did I say degrees? My apologies. What do I do in this situation? Still going to use which formula? The first formula. Again, we know that because we're in radians. But this time we have to solve for r. So if I divide both sides by 2.3, I get that 8.451 is approximately r. Everybody okay with that? So suppose we want to find the perimeter of a sector with a central angle of 17 or 1.7 radians cut from a circle with a radius of 5 centimeters. So a couple of pieces of vocabulary to kind of unpack and review before we get started on this. The first word is this word perimeter. What does the word perimeter mean? So in general, if you're not to describe the perimeter using a formula, if you're just going to describe what it is, okay, it's the distance around the figure, sure. The outside border, sure. Those are all good descriptors, okay? When we say sector, what do we mean by sector? A sector is a shape from geometry. It's basically like a slice of pizza. Okay? So when you hear the word sector, you should think slice of pizza. So to give us some help, I'm going to refer to these sides as A, B, or those vertices as A, B, and C. So in order then to find the perimeter, I need to take AB plus AC plus the measure of arc BC. Everybody agree with that? What is the length of AB? It's not 1, it's 5. Because we know the circle has a radius of 5. And I know when I cut my slice of pizza, we're cutting where the point is at the center of our circle, right? Anybody cut pizza before for a living? I guess when I say pizza, I mean like round pizzas, not these wacky Jets pizzas. Huh? Okay. Anyways, they artificially turned it into 2 square pizzas to create 8 corners. There's really just 4 corners. They just have 2 pizzas for 1. You guys can go to Jets and order an 8-corner pizza, and you can see what we're talking about. I mean, there's not 8 corners to it. It's 2. It's 2 pizzas. There's 8 corner slices. There's not actually 8 corners to the pizza. Here's the thing to make everybody outraged is I hate the corner pizzas. Moving on.
I'm with you on that.
But I also prefer round pizza to square pizza. All right. Okay. This is too much pizza talk for somebody that just got back from lunch, so let's move on. The one part to calculate the perimeter, we have 2 of the 3 parts concluded, right? What do we still need to find? Arc BC. How are we going to do that? So I know that this is 1.7 radian. So I can say S is equal to R times theta. Right? So I have, at the end of the day, that my perimeter is 18.5 centimeters. Everybody happy with that? Again, was it really any different than the things we were doing before? No, right? We just had this additional picture. Okay, so last example from this section. Stop talking, please. It says a car has 18-inch diameter tires on it. If the car is traveling at 15 miles per hour, how many revolutions per second are the tires making? So, notice that the unit that we're asked for is revolutions per second, right? What kind of a number is revolutions per second? It's a rate.
Wow.
Are we given another rate in this problem? 15 miles per hour. So my goal then is going to be to convert 15 miles per hour into some number of revolutions per second. Everybody okay with that plan? Okay. So I will start by writing 15 miles per hour as a fraction. And I know at the end I want to get something revolutions per second at the end. And I'm going to do this big long conversion in between. So first part, let's do the easy part. We need to convert the denominator from hours into seconds. So that should be pretty easy to do. How do I convert hours to seconds?
Divided by 3,600.
So let's convert hours to minutes next. How many minutes are in 1 hour? 60. So I know that when I write these conversion factors, the same unit has to be on a diagonal from each other. So what unit should be in my numerator? Hours. And I know 1 hour is 60 minutes. So after I multiply that first conversion factor, hours have canceled out, and we're now in minutes. It's exactly like chemistry. My next conversion, stop talking please, I'm going to convert from minutes into seconds. So how many minutes are in it, or how many seconds are in a minute? 60. What unit should be in my numerator? Okay, and I know there's 1 minute in 60 seconds. Everybody good here? So we're now, stop talking please. Stop talking please. Our final answer is now in seconds. The catch here is, though, we still need to convert miles into revolutions. And maybe that's not entirely clear what the relationship between linear distance and a revolution is. So let's think about this for a moment. Suppose we have a flat surface, and we have a wheel sitting on that flat surface. So we start here, and the wheel turns. And does that, right? Everybody's okay with that? Okay, the question then becomes is, how far is that? It is 1 circumference of our circle. Right? So imagine if I severed my circle right here and I laid that distance down, that would be our observation. So I know that 1 circumference equals 1 revolution. What is the circumference of the wheel in our case? 18 pi. Remember, circumference is 2 pi r. So since our diameter is 18 inches, our radius is 9 inches. So 2 times 9 times pi is 18 pi. The diameter in our case is 18 inches, so the radius is 9. 2 times 9 times pi is 18 pi. So notice that the unit here is in inches. Right now, our linear distance unit is in miles, so before we can apply this conversion factor, we should convert miles to inches. I don't know that conversion for miles directly to inches, but I know how to get there. What should we convert miles to first? Feet. How many feet are in a mile? 5,280 feet in 1 mile. And then from feet, we can convert this to inches. 12 inches in a foot. And so the feet cancel. And now since we're in inches, we can apply this last conversion. So I know 18 pi inches is 1 revolution. Everybody okay with this conversion that we've just done? Okay, I'm going to... No, miles and miles cancel out. The very beginning problem?
Oh, I see it.
Where it says 15 miles per hour? That's okay. So to type this into my calculator, I'm going to just type it in as one gigantic fraction, where I'm going to type in the numerator together. So 15 times 1 times 1, you don't really have to type the ones in, times 5,280 times 12 times 1. And in the denominator, I'm going to have 1 times 60 times 60 times 1 times 1 times 18 pi. So I get about 4.669 revolutions per second. Any questions about this first section? Hopefully this all felt pretty easy, right? We didn't really do anything complicated here. This last question was a little bit challenging, but it really is just a unit conversion problem that you've done many, many times before, right? You guys have done similarly complicated things before in your science classes, right? We're going to now start section 2. Yeah, it's okay, guys. I can take a look at what you typed in after class and we'll figure it out, okay? Oh. Yes. 7-ish? Yep. Again, new schedule, so we'll see what we're able to do. But
Hi, Mr. Kulik. Love you.
You guys are weird. All right.
That's on there. Everyone check.
So, section 2, stop talking, please. Stop talking, please. We're going to return back to our right triangle definition for our trigonometric functions. So, from your geometry class, I think every single person, when we talked about geometry topics at the beginning of the year, said they remembered SOHCAHTOA. So, when we say sine theta, what is sine equal to? Opposite over hypotenuse. Okay? And then cosine is equal to? adjacent over hypotenuse. And tangent is equal to opposite over adjacent So there's SOHCAHTOA. Stop talking, please. We also, in this course, are going to be concerned with 3 other trigonometric functions. So these are referred to as the reciprocal identities. So the first one we're going to talk about is cosecant, which is abbreviated as SC8 or CSC, which is hypotenuse over opposite. The second one we'll talk about is secant, which is abbreviated SEC, which is hypotenuse over adjacent. And the third one we're going to talk about is cotangent, which we abbreviate as COT, which is adjacent over opposite. Why do you suppose we call these the reciprocal trig functions? Because they're literally a reciprocal of one of our primary 3 trig functions, right? Cosecant is the reciprocal of sine, secant is the reciprocal of cosine, and cotangent is the reciprocal of tangent. The way that I remember this is that no cos go together. So sine, so cosine reciprocal is secant, because the other 2 start with cos. And then if I remember that, the other 2 are easy to remember because the tangent fit together. Everybody okay with that idea? Okay. So suppose that I wanted to find all 6 values for theta in this situation. So let's say we want to find the exact value. Let's be more specific. So let's say we want to start by finding the exact value for sine theta. Do I have enough information to do this currently? No. What do I still need? The hypotenuse. How can I figure out what the hypotenuse is? I can use the Pythagorean Theorem. Good. What is the Pythagorean Theorem again? Good. It's supposed to be for all 6. Sorry. Okay. Everybody feel okay here? So far, so good? Now that you've picked apart all my little misspellings, all 6. All 6. That's right. That's okay. All right. So, what is the value for sine theta then? Good. 5 over the square root of 29. Is this the way that we're going to leave our final answer? No. So remember you guys had asked about rationalizing denominators earlier when we were doing some other simplifying? And I said that I wouldn't worry about it until I told you to worry about it. This is now when we're going to worry about it. So in a case where you have numbers, you should rationalize a denominator if the fraction contains only numbers. So what do we need to do to rationalize this denominator? Multiply the top and bottom by the square root of 29. Everybody okay there? What's cosine of theta then going to be? Good, 2 over the square root of 29. But really, how should I write that? Good. And then if I want to do tangent, should I write for tangent? What's the answer for tangent? 5 over 2 or 5 halves. Good. And I don't have to do anything there with that. Okay? All right. So let's now write the values for cosecant theta, secant theta, and cotangent theta. What's the value for cosecant theta? Good. Do I have to do anything to that?
No.
No. Good. For secant. Good. And then for cotangent? Good. Everybody good with that? How are we spelling 2/5? With an F. Yeah, with an F. Oh, as an aside here, since we're talking about spelling, how do you spell the word vertical? I would say a quarter of the class ends vertical with ICLE. So, okay, let's do another example. So, let theta be an acute angle in a right triangle. If sine theta equals 1/3, find the find the values of the other 5 trig ratios. What should be my first step in a problem like this? Draw a picture. So we know there's a right triangle. And I'm going to label one of the sides as, or one of the angles as theta. Does it matter which angle I label as theta?
No.
As long as it's not the right angle, it doesn't matter. Okay? So, what should I do now? So I've drawn a picture. Good. So, which side can I label? Okay, the hypotenuse is 3. What else can I do? Opposite side should be 1. Okay. How do I figure out the third? Good. Oh, no. Okay. 1 squared plus b squared equals 3 squared. So b is going to be the square root of 8. It does simplify to 2 root 2. And once we have this, Three squared is 9, minus 1 is 8, square root of 8 is 2 root 2. All right. So what is the value for cosine here? Yeah, let's write it as 2 root 2 over 3. The value for tangent is okay. Is that the way we're going to write our final answer? No. What do we need to do?
Rationalize the denominator.
Okay. What should I multiply the top and bottom by? Just square root 2. You could multiply it by 2 root 2. You'll just have more reducing to do at the end. When I do that, I get square root 2 on top and 4 on bottom. Okay? Cosecant. What is that? How about secant? Oh, shoot. That's not right. Okay with that? All right. Next up.
Can you go back?
Stop talking, please. The next thing I want to talk about is finding exact values for these trigonometric ratios. When can we find exact values? Is when theta is 30 degrees, 45 degrees, or 60 degrees, because we can revert to using our special right triangles. They were, but you weren't given an angle measure in any of those situations. Oops. Maybe we'll do X. That's pretty poor. Pretty poor, Kulak. Raul. We haven't talked about what the unit circle is yet, so we're not making any assumption about unit circleness. So we can literally leave them this way and just use these triangles as we've drawn them. Yeah, that's fine. You can make the x1 if you want. That's fine. All right. So if I want to find sine of 30 degrees then, what would I get? If I want to do cosine of 45, what would I get? X over the square, or x squared root of 2, which is reduces to 1 over the square root of 2, or, I'm sorry, root 2 over 2. Everybody feel okay with these? What do you do if we're asking for sine of, say, 17 degrees? How would I do that? Yeah, that's exactly right. Just, you got to use your calculator. Yeah, I forgot the la. What do you have to be careful about here, though? What mode should your calculator be in to do that above problem? Degrees. So just to remind you guys, firing up your calculator, if you press the mode button here next to the second, you can check to see if it's in radian or degree mode. Make sure that you're in the correct mode. You will have to switch back in between modes in this class frequently.
That's so much fun.
If you are getting answers that don't make any sense, the most likely culprit is wrong mode. What? So, for example, if I forgot to check the mode, and I type in sine of 17, look at the number that I'm getting. Does this number make any kind of sense? No. 17 degrees is an angle inside of a right triangle. How the heck am I getting a negative number here? It's the wrong mode. It is the wrong mode. Topic here. The last topic is if I ask you to solve the triangle. What does this mean? Yes. It's finding all the angles and all the side lengths. Okay. So let's give this triangle some name here. What would you like to do first? Find the other angle C? Great. What is it? So that is 49, right? Everybody agree with that? Great. Now what? Let's find one of the three sides. Which side do you want to look for? CA. Okay, I'm going to call that X for our sake. So what I'm looking for then, now we need to pick an angle. Which angle do you want to use? 41. Okay. So we need a trig ratio that includes opposite and adjacent. So I should use tangent of 41 equals X, which is opposite, over 12. Everybody good with that? Okay. To solve for X, I multiply both sides by 12. And then I just type this into my calculator. Let me change my mode real quick, though. $10.431. Okay. How can I find AB, or CB, excuse me? Okay, is that the best way to do it, the Pythagorean Theorem? Why is that not going to be the best way? You're using a rounded answer to get another answer that you're going to round. Is there a way to do it without having to use a rounded answer? Yes. What could I do? Good. I can do cosine of 41, which is adjacent over hypotenuse. So to solve this, I'll multiply both sides by y, and then divide by cosine of 41. And then I can type that into my calculator. When I do that, I get 15.99 or 900. Oops, approximately. Okay. For you guys, the homework I'm